It's a cold chamber. It's actually cold on the bottom, very cold, about -40 on the bottom and about +40 on top.
So in some sense, this machine is trying to replicate what happens inside a snow cloud.
In a sense, that's right. I mean, it's not hard to grow ice crystals. All you need is cold and water.
In the freezing conditions of the chamber, we should be able to see the inherent geometry of the world emerging in front of our eyes as the crystals start to form.
And now, with any luck, we will see some stars growing on the ends of those needles.
As the temperature drops, billions of water molecules coalesce out of the vapor, spontaneously arranging themselves into these 6 pointed patterns. At least, that's the theory. But the reality turns out to be very different. As Ken found out, even in laboratory conditions, it's almost impossible to grow perfect snowflakes.
I don't think any of these are symmetrical, so no, not a single one. Look at that.
What's the chance of getting a perfectly symmetrical snowflake inside here?
The really beautiful photogenic snowflakes are really about 1 in a million. I mean, they're
Really? Wow.
sometimes they've got 5 sides or 3
5
sides.
sides? Oh, no.
or 3, or sometimes you get a blob. It's a little hard to see, but this mess here is one funny-looking snowflake.
We do tend to think of the snowflake as something which is beautifully symmetrical, but actually that's just some idealized notion, and the reality is that they're actually much more complex and irregular than we think they are.
At the molecular scale, it's quite perfect, but as the crystal gets bigger,
Yeah.
the atoms don't hook on always exactly the right way, so when it grows, how it grows depends on the environment, the temperature and the humidity. So it starts growing one way, and then it moves to a different spot in the cloud and grows a different way, and then a different way and a different way. And so by the time the crystal hits the ground, it's had a very complex growth history, and so it ends up as a very complex crystal. Oh, there it goes.
It seems that you can only come so far in trying to describe the world with simple geometry. You can see it at work in the salt crystals in the crystal cave, but in truth, that's one of the very few places in the world where you'll find such crystals. The bees use simple geometry to make their honeycomb, but they've evolved to perform that task over many thousands of years. And it's only occasionally that you'll ever find a purely symmetrical snowflake.
Because although everything is formed from tidy geometry at the atomic level, that underlying order falls apart amid all the competing forces of our chaotic world. Even the Giant's Causeway isn't really a neat hexagonal array.
It's almost there, but amongst the hexagons, there are pentagons, 7-sided columns, even a few with 8 sides. That network of perfectly interlocking hexagons just doesn't exist.
The world clearly isn't just built from simple geometric shapes. The movement of the sea and the flow of the waves are far too complicated to explain in these terms. It's difficult to imagine how we could ever find a code to explain all this complexity.
But what if there are patterns to the chaos of nature? Patterns that we're not aware of, but that we're attuned to on a subconscious level? This barn was home to one of the artistic revolutions of the 20th century. The painter who worked here had become disillusioned with conventional painting techniques. In fact, he stopped painting altogether and started splattering.
He was as controversial as the art he produced. An arrogant, self-destructive drunk, and perhaps a visionary. His name was Jackson Pollock.
The floor, you can still see, is covered in paint. What Pollock would do is to lay a canvas out on the floor. And then, often intoxicated, he would drip and flick the paint all over the surface. He'd come back week after week, adding more and more layers, more and more colours. The result was extraordinary. There were huge outbursts of abstract expressionism, just covered in paint, scattered all over the place.
Pollock's paintings sent shockwaves through the art world. No one had ever seen anything like this before. Life magazine declared him Artist of the Century. Others derided his efforts as the substandard dross of a drunken lunatic. But though Pollock's paintings courted controversy, they were incredibly influential. Not least because the apparent random squiggles are strangely compelling.
Many people have tried to copy Pollock's techniques, some in homage, others in attempted forgeries. But nobody seems to be able to reproduce that magic that Pollock brought to the originals.
Pollock's paintings seem to have captured something of the wildness of the natural world. But for a long time, no one could define exactly what it was that made his work so appealing. Until it came to the attention of artist and physicist Richard Taylor. His unique approach was to invent a machine that could mimic Pollock's eccentric painting style.
It's all based on this apparatus called the Pollockizer.
The Pollockizer, that's lovely.
Now what it is essentially though is what's called a kicked pendulum. And as you know, a basic pendulum is very, very regular like a clock. But at the top here, what you've got is a little device that can actually knock the string as it's swinging around. And that induces a very different type of motion called chaotic motion.
So this would be like Pollock's hand. This would be what he'd be trying to achieve with that sort of off-balance painting that we do.
Absolutely. So they're very similar processes.
It's very effective.
By recreating his technique, the Pollockizer is able to mimic one particular aspect of the artist's work. And that is that it appears more or less the same, no matter how closely you look.
You keep on seeing these patterns unfolding in front of you. And with a Pollock painting, all of those patterns at different size scales look the same.
This is a property known as fractal.
So if I took pictures at these different scales and showed them to somebody, in some sense they wouldn't be able to tell which one was the close and which one was far away.
Absolutely. So as long as you can't see that canvas edge, then you have no idea whether you're standing 30 feet away or 2 feet away. They'll both have exactly the same level of complexity.
More than any other painter, Jackson Pollock was able to consistently repeat the same level of complexity at different scales throughout his paintings. The fractal quality of his work appeals to us because despite seeming abstract, it actually mirrors the reality of the world around us.
When we started to actually analyse the buried patterns in there, this amazing thing emerged. Deep down hidden in there is this level of mathematical structure.
So there's this really delicate interplay between something that looks messy and chaotic, but actually it has structure and some underlying code hidden inside it.
Absolutely, and you can see it not only in his paintings, but you see it everywhere. You know, like a tree outside, you look at the tree from far away, you see this big trunk with a few branches going off. Superficially, they look cluttered and they look incredibly complex. but your eye can sense that there's a sort of underlying mathematical structure to it all. Pollock was the first person to actually put it on canvas in a direct fashion that no other artist has ever done. It really is the basic fingerprint of nature.
And that's what's most fascinating about Pollock's art. In creating works devoid of conventional meaning, he had in fact stumbled across something fundamental. Because fractals are how nature builds the world. Clouds are fractal because they display the same quality. Giant clouds are identical to tiny ones. And it's the same with rocks. From appearances, you can't tell if you're looking at an enormous mountain or a humble boulder. And then there are living fractals, like this tree.
It's quite easy to see how fractal it is, because if you take one of the branches, it looks remarkably like a small version of the tree itself. And if you look at the twigs coming off the branch, they have the same shape. So you see the same pattern appearing again and again at smaller and smaller scales.
And trees also demonstrate the great powers of fractal systems. Their great complexity stems from very simple rules.
Now, the reason the tree makes this shape is because it wants to maximize the amount of sunlight it gets. Very clever, but also very simple, because you just need one rule to create this shape. What the tree does is to grow, then divide, grow, then divide. And by using this one rule, we get this incredibly complex shape we call a tree.
Even in laboratory conditions, it's almost impossible to grow perfect snowflakes.
I don't think any of these are symmetrical, so no, not a single one. Look at that.
What's the chance of getting a perfectly symmetrical snowflake inside here?
The really beautiful photogenic snowflakes are really about one of the...
As the temperature drops, billions of water molecules coalesce out of the vapor, spontaneously arranging themselves into these 6 pointed patterns. At least, that's the theory. But the reality turns out to be very different. As Ken found out, in the freezing conditions of the chamber, we should be able to see the inherent geometry of the world emerging in front of our eyes as the crystals start to form.
And now, with any luck, we will see some stars growing on the ends of those needles. A million, I mean, they're...
Really? Wow.
Sometimes they've got 5 sides or 3
5
sides.
sides? Oh, no.
or 3, or sometimes you get a blob. It's a little hard to see, but this mess here is one funny looking snowflake.
We do tend to think of the snowflake.
It's a cold chamber. It's actually cold on the bottom, very cold, about -40 on the bottom and about +40 on top.
So in some sense, this machine is trying to replicate what happens inside a snow cloud.
In a sense, that's right. I mean, it's not hard to grow ice crystals. All you need is cold and water.